Hey everyone! In this video, we're going to be taking a look at how to use the chain rule when dealing with multiple composite functions. So we've already talked about the chain rule and how to use it with composite functions that are made up of two functions. But now what if we add more functions into our composite function? We're going to take a look at how to do that using the chain rule. So first, just a reminder, the chain rule, if we have a function, let's say y is equal to f of u, and we have another function u where this is equal to g of x. So here we are taking the function g of x and we're putting it into the function u. Remember, we have other notation for this as well. So f of g of x, this is equal to f, and we're putting g of x inside that function f of x. Then our derivative, so the derivative of y prime, this is going to be equal to the derivative of y with respect to u times the derivative of u with respect to x. So in other words, it's the derivative of the outside function times the derivative of the inside function. But now let's say we're going to add in another function, another equation. So let's say we have y is equal to f of u, and we have another one, u is equal to g of some variable v. And then lastly, let's say we have our last one where v is equal to some function h of x. So now we have three different equations. And if I kind of take a look at this, h of x is going into g, and then g is going into the function f. So in our other notation, this would be f of g of h of x. Or in other words, we have f, g, the function g is going to go into f, and inside the function g we have h. So three functions now, so it's a multiple composite function. The chain rule can be applied to this as well. In this case, our derivative y prime is going to be equal to dy over du, so the derivative of y with respect to u times the derivative of u with respect to v times the derivative of v with respect to x. So it's very similar to our original chain rule, except we're just adding one more fraction. So we're taking the derivative of the outside, the derivative of the next step on the inside, and then finally the derivative of the very inside. If I take a look at my notation here, so this is written in Leibniz notation, but if we take a look, we have a du in the numerator here and a du in the denominator here. So those cancel out and they simplify. Same thing, we have a dv over dv, which will simplify. And if we do that, we're left with dy over dx, which is our notation representing the derivative. Okay, so the derivative of multiple composite functions, using the chain rule, all we're doing is just extending it a little bit further. So let's use this in an example just to apply it, and we can see how this process goes. Okay, so my example, I have this equation y is equal to 5 times the cosine squared of 3x plus 2. The first thing to note here is when I have cosine squared like this, remember that can be rewritten. So I can rewrite this actually as 5 times the cosine of 3x plus 2, and that whole thing is squared. So we can put that squared in multiple locations. But what I'd like to do is I want to rewrite this as a composite function. So I want to break this down into the three different parts that make up my equation y. So the first thing, I'm going to say let v equal what is inside my parentheses. So v is equal to 3x plus 2. If I set it up like that, then I can rewrite my equation. Then y is going to be equal to 5 times the cosine squared of v. Right? But I still have multiple things going on. So let's do one more substitution here. So let's define the variable u, and I'm going to let u be equal to the cosine of v. So if I do that, now I can rewrite my equation. Y is equal to 5 times u squared. So I have my three different parts here. So breaking down my composite function, what I'm doing is I have something that's squared, and then I also have something that I'm taking the cosine of. So then my derivative, so y prime, this is going to be equal to the derivative of each of these parts. So the derivative of y with respect to u, because that's the variable we have in our equation of y now. And we're going to do the derivative of u with respect to v. And we'll also do the derivative of v with respect to x. So again, we're finding the derivative of the outside, and then we're working our way in, finding the derivative of each part. So the derivative of our first part, so the derivative of y. So here we'll use our power rule. So the 2 will come down. So 5 times 2, we end up with 10u. And then let's back substitute. So replacing the u with what we substituted out. So this ends up being 10 times the cosine of v. And we'll do one more piece of substitution here, plugging back in what we had for v. So we end up with 10 times the cosine of 3x plus 2. All right, moving on to our second piece, du over dv. So now the derivative of u, the derivative of cosine, is equal to negative sine. And then again, we'll do a little bit of back substitution. So plugging in what we had for v, we get negative sine of 3x plus 2. And our last one, so the derivative of v with respect to x, the derivative of 3x plus 2, we just end up with 3. So now to finish this up, to find our derivative, we just need to multiply all three of those pieces together. So the derivative of y, this is going to be equal to 10 times the cosine of 3x plus 2 times negative sine of 3x plus 2 times 3. And let's just do a little bit of simplifying to finish up. So I have 10, I have a negative 1, and I have a 3. Multiplying those together, we get negative 30 cosine of 3x plus 2 sine of 3x plus 2. So again, the chain rule when we're dealing with multiple composite functions, it's very similar to our original chain rule, but now since there's an extra function in here, there's an extra derivative that we're finding. But it's still the same logic. We find the derivative of the outside, find the derivative of the next step inside, and then we find the derivative of the very inside. And that's it.